Hello and welcome to this presentation related to an introduction to dimensional analysis. In this presentation we're going to consider the use of dimensions when analysing various equations, and we'll be using the dimensions of m, l and t throughout the presentation. Here's an overview of the presentation related to dimensional analysis, particularly the use of dimensions. We commence with an introduction outlining the purpose of dimensional analysis. We recap the SI base units and we introduce dimensions of m, l, t and theta that relates to mass, length, time and temperature respectively. We then have example 1a where we're finding dimensions of constant r in the equation PV equals mRT. Example 1a essentially sets the scene to show the kind of questions we'll be considering later in the presentation. Then we have a section relating to practicing the laws and the rules of indices. There's some various exercises. If you want to attempt these, you're welcome to. Some of the solutions I'll work through fully for you. But again, it's just to make you more proficient with the use of the laws and the rules of indices, because we'll need that proficiency within some of the solutions. Then we have a table of SI derived units. This will essentially form a very important database to help underpin the various solutions we will undertake within the presentation. So I'd encourage you to spend some time developing the database because we will refer to it extensively throughout the presentation. Next we have the principle of dimensional homogeneity. We outline the implications of this principle and its application. Then we have a series of examples. Example 2a, we're checking the equation given here for dimensional homogeneity. Example 3a, we're determining the unit of mu in the equation given, which relates to fluid mechanics. Example 4a, determine the dimensions of k, it's a constant in the equation F equals kv squared. Example 5a, we find the exponent value of a in the equation shown here. Example 6a, we find the exponent value x in the equation t is equal to mk to the x. And finally we finish with some exercises where I will show you the full work solutions, although I let you review them at your own pace, and I leave you with some questions to attempt. And here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note all times are rounded to the nearest minute. An overview of dimensions. Many problems in engineering and particularly in thermofluid mechanics involve complex relationships between quantities, for example fluid flow, for which it is not always possible to find a purely analytical solution, and thus experimental methods are used to find relationships between the variables. The results of these experiments, for example measuring the drag force on a motor car or on a model aircraft in a wind tunnel, are most clearly represented and interpreted if they are stated in dimensionless form. The various parameters in a problem are grouped together in such a way that they form a certain number of dimensionless groups. That is written as dimensions m to the 0, l to the 0, t to the 0, or simply as 1. There are several mathematical techniques that can be used to achieve these dimensionless groups. We'll just review one technique within this presentation. Dimensions continued, a technique which goes some way towards finding the relationships and also gives a clear indication of how to present experimental information, is called dimensional analysis, which will be developed later. Initially, some fundamental ideas must be considered. Engineering uses quantities which are built up from a basic set of dimensions, each dimension in the set being separate and independent from each other, for example mass, length, time, etc. Note that the word dimension used here does not only have the usual meaning of linear dimension. Dimensions continued. The SI base units and symbol used to denote the dimension are stated below. Note the international system, i.e. the Système International or SI, of units has 7 base units, also referred to as primary standards. But in mechanical engineering, the first 4 are mainly used. Table 1 below shows the 4 base SI units we'll be considering within this presentation. So the first quantity is length. That has the SI unit of the meter, symbol lowercase m, and the dimension stated as uppercase L. Second quantity is mass, which has the unit of the kilogram, symbol lowercase kg, and dimension uppercase m. Third quantity is time, SI unit the second, symbol lowercase s, and dimension uppercase t. And finally temperature has the SI unit of the Kelvin, symbol uppercase K, and dimension theta. Notice that all the dimensions are stated in square brackets, and we must always state our dimensions in square brackets to clearly differentiate them from the actual calculations and the algebraic variables we might use within a calculation. Here's a general note related to the expression the SI system. Technically speaking, the expression SI system is non-preferable because it contains a redundancy, as SI stands for Système International d'Unité, which translates to the International System of Units. Thus, stating the SI system is essentially saying the International System, and thus the redundancy. However, in practice, the expression SI system is widely used and understood, especially in informal situations or in teaching environments. However, within academic or professional writing, it is preferable to state SI units or SI or the International System of Units. So I said that's just for a general note, and in truth I often do refer to the SI system, but just for completeness we should be aware that it's preferable to state SI units or the International System of Units. Dimensions continued. From this basic set, dimensions of other quantities are found in one of 2 ways. Firstly, through definition. For example, velocity is defined as the rate of change of distance with time. So the dimensions of velocity are, distance would be in meters, having dimension L, and time would be in seconds, having dimension t. So L divided by t would be the dimension of velocity. We often write that in terms of the negative indice, so L divided by t could be written as L multiplied by t to the negative 1. Again, notice the use of square brackets to define the dimensions. Second way of finding the dimensions is through a physical law. For example, force is stated by Newton's second law, F equals ma, for constant mass systems. So the dimensions for force relate to the equation. Mass is in kilograms, that would be uppercase m as a dimension, and acceleration is meters per second squared. So again, in terms of dimensions, that would be L divided by t squared. Often we write ml divided by t squared as mlt to the negative 2, again in the square bracket. Dimensions continued. So using the above approach, the quantities commonly used within mechanical engineering can be considered with their dimensions in terms of the basic set of m, l, t and theta. Note within this work, the laws and the rules of indices will be required to help simplify dimensional quantities. And for your reference, these laws and rules are shown on the adjacent table. So here are the laws and the rules of indices. And purely for reference, here are the common SI base units and dimensional symbols, including quantities we will not be considering within this presentation. It just shows the notation used for the respective dimension. Let's consider example 1. This is going to illustrate the kind of problems we're going to be considering later in the presentation, so it's just setting the scene here. So from the perfect gas law, written as PV is equal to mRT, we've got to determine the dimensions of gas constant R and state what the SI unit of R would be. So extracting the information from the question, we know PV is equal to mRT. I'm going to rearrange this for the gas constant, symbol R. So in other words, dividing both sides by m and t, on the right hand side we have PV divided by mt. Next we're going to consider the SI units and dimensions of the quantities, P for pressure, V for volume, M for mass, and T for temperature. So let's consider pressure first of all, pressure capital P. Now pressure is defined as force divided by area, and in simple terms that would be N for Newton divided by areas in meters squared. But the Newton in base units is stated as kilogram meter per second squared. From Newton's second law, F equals ma. That's still divided by m squared, of course. So simplifying, we cancel the m in the top line with an m in the bottom line to show that pressure is actually kilogram per meter per second squared. As I say, we often write these expressions in terms of the negative indices, so P could be written as kilogram meter to the negative 1, second to the negative 2. Now we have pressure in terms of SI base units, we can write down the dimensions, and the dimensions of pressure would be M for the kilogram, L to the negative 1, for meter to negative 1. So seconds S to negative 2 becomes in dimensions T to the negative 2. So again, using our square brackets, we define the dimension for pressure. The unit of volume is more easy to define. We know that the volume is meter cubed, so in terms of dimensions, that would simply be L to the 3, L cubed. Mass, lowercase m here, would have the unit of the kilogram, so capital M for dimension. Finally, temperature, case T here, has the unit of the Kelvin, and in terms of dimensions, we write that as symbol theta in our square bracket. So now returning to the equation above, for R, written on 2 lines here, we're simply going to impose the dimensions for each of the quantities. So R is equal to pressure P, having the dimensions M, L negative 1, T negative 2, multiplied by the volume, having the dimension L cubed, divided by the mass, having the dimension capital M, and divided by the temperature, having dimension theta. Now all we do is use our laws of indices to simplify our expressions where possible, noting straight away that we could cancel the m on the top line with the m on the bottom line, and using our first law of indices here, L to the negative 1 multiplied by L cubed is written as L squared, and our T to the negative 2 remains as T to the negative 2, and that's all divided by theta. So that can be written now as L squared multiplied by T to the negative 2 multiplied by theta to negative 1, again using our reciprocal index here. So now we have the dimensions for quantity R. We can actually use any system to define our unit, so we could use the imperial system should we want to, but of course we're always going to use SI units here. So now I just translate the length squared from a dimension to the unit of meter squared. The dimension of T to negative 2 becomes the second to negative 2, S to negative 2. And the theta to negative 1 will translate as an SI unit into the Kelvin to negative 1. So that's our basic SI unit, meter squared, second to negative 2, Kelvin to negative 1. Or of course you could write that as the meter squared divided by the second squared Kelvin. So that's just an introductory example to show the kind of problems we're going to consider and how we're going to use dimensions to help us structure the solution. For your reference, if you're unsure on how we manipulated the kilogram meter per second squared divided by the meter squared into the final answer of kilogram meters to negative 1 seconds to negative 2, this extract from our previous presentation related to fractions shows the proof we use to undertake division of fractions. So if we're dividing the kilogram meter per second squared by meter squared over 1, That's effectively what we have here. Then from the above algebraic proof, that's the same as kilograms meters divided by seconds squared multiplied by the reciprocal of the denominator. So instead of having m squared divided by 1, I've written it 1 upon m squared. Now we can see that the meter in the top line cancel with the squared on the meter in the bottom line to leave us with kilograms per second squared meter, and I've just shown that in terms of the negative indices for the final answer. So again, I'm just showing this for reference, as some students do find the fraction manipulation quite difficult, especially when it's presented on one line, as I often do within these notes. For reference, this slide allows you to practice the laws and rules of indices. Exercise 1I just asks us to simplify the following expressions using the laws and the rules of indices, but without using a calculator. I've only included this in the presentation if you need further practice, but essentially question A will require the first law of indices. The first law of indices is shown here. Part B would also require the first law of indices to simplify. Part C is a first law problem, but notice it also involves the fractional indices, so it needs this rule here for writing a third in terms of a fractional index. So basically the square root of x is written as x to the half, but then we apply the first law. So questions D, E also require the first law. Question F is a first law problem, but note there are different quantities here. We have an M and an L quantity. You can only apply the laws of indices when the bases are the same, so we have two bases here, M and L. And again, be careful with G, same kind of thing here. It's a first law problem, but we've got different bases, X and Y. Question H is a first law problem in the numerator, but then it can become a second law problem because of the division required. So second law problem. And question I, J, K are all first and second law type problems. Question L is a third law problem, shown here. And question M, inside the bracket is essentially a second law problem, but notice it's raised to the power of 5, so of course that requires a third law. So if you want to attempt those questions, it should help you develop your applications of the laws and the rules of indices. I will show you the full work solutions for these questions on the following slides. So practicing the laws and the rules of indices, here are these solutions, question A through to question I. I'll let you review these at your own pace. And practicing the laws and rules of indices continued. Here are solutions, question J through to question M. Again, I'll let you review these at your own pace. Practicing the laws and the rules of indices continued here. And if you want to attempt further questions, we have questions N through to U here. But no work solutions are shown for these questions, although the answers are shown on the following slide. So practicing the laws and rules of indices continued. Here are the answers to all the questions for your reference. Let's consider exercise 1. Table 2 below lists some principal derived units used within engineering science. We're asked to complete the right-hand dimension column for all the quantities stated. This table spans several slides. Essentially what we're going to do now is develop a database that we'll be able to refer to within the various solutions to dimensional analysis problems we'll consider later on. So let's consider some of the quantities. The first one is area. The second column here just states the symbol generally used for area, usually uppercase A. The derived SI unit for area would be the meter squared, written as m to the power 2. And in terms of dimensions, that would be L to the power 2. We consider volume another derived unit, symbol uppercase V. The derived unit would be the meter cubed, m to the 3. So the dimension is L to the 3. If we consider the property of mass density, this is defined by the equation mass divided by volume. The usual symbol for density is lowercase rho, it's a Greek symbol, and it's a derived unit because it's formed by mass, which is the kilogram, and from above volume is the meter cubed, so it's kilogram per meter cubed. as the SI derived unit. In terms of dimensions, that would be m L to the negative 3. Now for the rest of the parameters in the table, I'd like you to consider and write down the dimensions of the derived unit. So distance, linear distance here, would usually have the symbol lowercase s in mechanics. The unit would be the meter, so the base unit here. So you need to now consider what would be the dimension of the meter. Then consider linear velocity, derived as distance divided by time. Then we have linear acceleration, derived by the formula velocity divided by time taken. And then gravitational acceleration, which we all know is 9.81 meters per second squared. So I'm going to let you think through what the dimensions are, and I encourage you to write them down in your notes. The table is continued on the following slides. Here's exercise 1 continued. We have more quantities for you to consider here, such as force, weight density, potential energy, power, pressure, and then direct stress and shear stress. Again, I would encourage you to write the dimension down. And exercise 1 continued. Here's the final slide of our table, and more quantities for you to consider here, ranging from torque through to kinematic viscosity. I have inserted some of the dimensions purely for reference. On the following slides, I will now show you the dimensions for all the quantities. So here's exercise 1, the solutions, our SI derived units. Here's our dimensions. You can now check your values against what's on the slide here. The right hand column where it states definition or law is purely for reference. We're not really concerned in this presentation whether we derived our quantities from a definition or a law. As I said, that column is purely for reference. Exercise 1, solutions, table 2, SI derived units continued. Here are more dimensions. For reference, you can check these against your own answers. Exercise 1, solutions continued. So our final slide showing dimensions for the final array of quantities. That concludes the database, but as I say, we'll refer to this extensively when we're solving the later problems posed to us. Let's consider the principle of dimensional homogeneity. An important principle in dimensional analysis is the principle of dimensional homogeneity in all equations, which states the following. In any equation which relates physical quantities as opposed to numerical quantities, each term of the equation must have the same dimensions. Note, units must also be the same and conform to a coherent system, such as the SI. Principle of dimensional homogeneity continued. Implications of this principle. If each term in an equation has the same dimensions, this implies that each of the fundamental dimensions, such as mass, length, and time, must have the same index. So this principle, and the dimensions we derived in our table 2 for each of the quantities, can be used within the following problems. A. To find the dimensions of a quantity in a given equation. B. To check the equation produced by an analysis to see if any errors are present in the derived equation. And C. To find an unknown index in a given expression. And within this presentation, we will now use dimensional analysis to solve these various types of problems. A question sometimes asked is why dimensions and not units are used in dimensional analysis. Dimensions are universal, whereas units are arbitrary. So dimensions, for example, length L, mass m, time t, describe the nature of a physical quantity. Units, for example, meters, kilograms, seconds, etc., are human-defined conventions used for measuring those dimensions. Dimensional analysis is concerned with the relationships between physical quantities, not the specific measurement system used. For example, velocity has the dimensions lt to the -1, which is true whether measured in meters per second, millimeters per second, kilometers an hour, feet per second, miles per hour, etc. So in other words, units of quantities can vary, but dimensions do not. The principle of dimensional homogeneity continued. Let's consider example 2. Newton's equation of motion states that for constant acceleration a, the distance travelled in time t is given by s is equal to ut plus a half at squared, where u is the initial velocity. We're asked to check the equation for dimensional homogeneity. So here's our solution. Given the above equation, we're now going to insert the respective dimensions. So on the left hand side for s, which of course is distance, that will have dimension uppercase L. U, we know above, is the initial velocity, dimensions lt -1, time taken, symbol lowercase t. That would be in seconds, of course, so that will have the dimension uppercase T here. And note, when we're considering dimensions, we ignore constants. So the half in the equation shown here will be ignored when we're considering dimensions. So the acceleration, lowercase a here, we know from our previous database, that would have dimensions lt to -2. And again, we have time, t squared in this case. So that would be dimension t to the power 2. So the dimensions for all these derived units are extracted from our table 2. Here's table 2 for reference, and here's distance, here's linear velocity, and here's linear acceleration. Those are our derived units showing the dimensions from our table 2. Time, of course, is a base unit. Now, for dimensional homogeneity, each of the three terms in the equation must have the same dimensions. So we clearly see the left-hand side of the equation has dimension L, so all the other terms must have L. And we can see this because for this term here, t to the -1 multiplied by t becomes t to the 0 or 1, so 1 times L is L. And for this term here, we have t to the -2 multiplied by t to the power 2 becomes again t to the 0 or 1, so 1 times L is L. So we can clearly see that each of the terms in the equation have the same dimensions, as they should if the equation is dimensionally homogeneous. Here's another example, example 3a. In fluid mechanics, Reynolds number, denoted Re, is equal to rho multiplied by U multiplied by L divided by mu. And this is a dimensionless property. We're given that rho is equal to mass density, U is equal to linear velocity, L is equal to lengths of pipe probably, and mu is equal to dynamic viscosity. So for part 1 of the problem, given the above information, we've got to determine the units of mu. Second part of the problem, we have to use the result from part 1 to show that Reynolds number is indeed dimensionless. But let's consider part 1 on this slide. So here's our solution, part 1. From the question, we're given Reynolds number. On the next line, I simply rearrange the equation to make mu the subject. So I've multiplied both sides by mu, divide both sides by Reynolds number. So now we have mu is equal to rho multiplied by U multiplied by L, all divided by Reynolds number. But of course Reynolds number is dimensionless, as stated in the question. So now referring back to our table 2, for rho, the mass density, that will be ml to -3. For linear velocity U, that will be lt to -1. And for the length, that will be L. Reynolds number is dimensionless, so we could ignore that from the equation, or in this case, just for completeness, I've shown it as 1 in a bracket. Again, referring back to table 2 and our derived units, here's the dimension for density, linear length, shown here in terms of distance, and the dimension for velocity. So again, we're just referring back to the table to extract the dimensions for the various properties within our problem. So simplifying, on the right hand side, we note we have L to the negative 3, L to the power 1, L to the power 1. Using the first law of indices, that simplifies to L to the negative 1. We still have the m dimension and the t to the negative 1 dimension. So for dynamic viscosity, symbol mu, the dimensions are m, L negative 1, t negative 1. If we now write that in terms of the SI unit for dynamic viscosity, the m becomes kilogram, the dimension L to negative 1 becomes a meter to negative 1, the dimension t to negative 1 becomes seconds to negative 1. So I've written the answer in terms of an SI unit, but actually when you know the dimensions of a quantity, you can write it into any system of unit you choose. Example 3 continued. This is part 2 now. It says using the result from part 1 on the previous slide, we've got to show that Reynolds number is indeed dimensionless. This is just really for practice of manipulating our equations using dimensions. So now considering the equation given for Reynolds number, rho u L divided by mu. On the next line I've simply written Reynolds number in the form of rho u L multiplied by mu to the negative 1, just using my reciprocal rule of indices here. What we do now is insert the appropriate dimensions for each of the quantities into the equation. So here's the dimension for rho, or u, or L, and now for dynamic viscosity, noting it's to the power of negative 1. On the next line, all I've done is raise the right hand bracket here to the power of negative 1. This is a third law of indices problem. So I write it as m to the negative 1, L to the 1, and t to the 1. On the next line, I simply multiply the two L's together here to produce L squared. And the final line, effectively, I bring my like terms together. So we have m to the 1 multiply m to the negative 1. We have L to the negative 3 multiplied by L multiply L to 2. And then we have t to the negative 1 multiplied by t. I think it's clear to see that multiplying the m's together becomes m to the 0, shown here. L to the negative 3 times L to the 2 is L to the 0. And t to the negative 1 multiplied by t is t to the 0. Remember that anything to the power of 0 is actually numerically 1, so we can see that the Reynolds number is dimensionless. That concludes the solutions to example 3a. Let's consider example 4a. In a simple relationship to calculate the aerodynamic drag, the drag force uppercase F is related to the velocity of the object, v, by the relationship F is equal to k multiplied by v squared. We're asked to determine the dimensions of k to satisfy dimensional homogeneity. So given that force F is equal to k multiplied by v squared, and noting that for dimensional homogeneity, the unit of F must be the same as the unit of kv squared, we firstly rearrange the equation for k, dividing both sides by v squared, so k is equal to F divided by v squared. We now insert the dimensions for F and v squared, and again we can refer back to our table 2 for the dimensions. Here's again a recap from our table 2 showing derived units, and here are the dimensions of force and the dimensions for velocity from table 2, which we simply insert into our equation. Notice it's velocity squared here. On the next line I simply use the third law of indices on the v squared bracket, so we have L squared t to the negative 2. We can now clearly see that the t to the negative 2 on the top line cancels with t to the negative 2 on the bottom line, and the L on the top line will cancel with the squared on the L term on the bottom line. Example 4a continued. Just for clarity, I'm showing you the cancelling here on two lines. So in our numerator we have ml to the 1 t to the negative 2 divided by l to the 2 t to the negative 2. So we can clearly see the t to the negative 2 in the numerator cancels with the t to the negative 2 in the denominator, and the l to the 1 in the numerator cancels with the squared term in the denominator to leave us with l to the power 1. Hence we end up with m divided by l. As I say, sometimes easier to understand the cancelling operations here when expressed in two-line formatting. So we're left with the dimensions of k being ml to the negative 1. So in other words, m divided by l. Writing in terms of an SI unit, k has the SI unit of the kilogram meter negative 1, or kilogram per meter. Let's consider example 5a. We're asked to find the value of the exponent a in the equation given, where eta is equal to 4 multiplied by qp, and that's all divided by pi multiplied by d to the power of a multiplied by l multiplied by n. We're given that eta is dimensionless. Eta is usually efficiency, which is dimensionless. qp has the SI unit of the meter cubed per second. Quantity lowercase d has the unit of the meter. Quantity L has the unit of the meter. And quantity N is dimensionless. Let's consider the solution to question 5a. I suggest the first thing we do here is determine the dimensions for quantity qp. So qp, we're informed, has the SI unit of the meter cubed per second. And in dimensions that would be L cubed multiplied by t to the negative 1. For the quantity d has the unit of the meter, so that will be dimension L. And for quantity L has the unit of the meter, that's dimension L. And efficiency is dimensionless, has a unit of 1. I'm not going to consider lowercase n because we're told n is dimensionless, so I'm not going to consider that in the equation. Well, we do need to consider eta because it's on the left hand side of the equation. So now inserting our dimensions for eta, for qp, for d raised to the power of a of course, and for l. On the next line I simply cancel the l in the denominator with the l cubed here to leave us with l squared, which is shown here. On the next line I simply multiply both sides by l to the power of a. And now we're going to use a process known as equating indices between the left hand and right hand side of the equations. And we can do this, equate indices for any of the dimensions that will help us form an equation. In this particular case, only dimension L, or length, will help us form the equation. So what we do now is literally consider the index associated with L terms on the left hand side and L terms on the right hand side. So on the left hand side we have L to the power of a, so we write down a on the left hand side of our equation, and on the right hand side we have L to the power of 2, so we write 2 on the right hand side of the equation. Now that's directly solved for a in this case is going to be 2. So the final part of the solution is simply to rewrite the equation for eta, but now replacing the a in the original question with the 2 we just evaluated through our equating indices process. So that's the solution to example 5a. Here's example 6a. I'm going to outline this for you and allow you a chance to solve this before reviewing the solutions on the following slide. The solution to example 6a is quite similar to that from example 5a. So from an experiment, the torque, capital T, in Newton meters, applied to a rotating mass, m in kilograms, was found to be related by the formula of T is equal to mk to the power of x multiplied by alpha, where k is termed the radius, having the unit of the meter, and alpha is the angular acceleration in radians per second squared. So using dimensional homogeneity, we've got to find the value of the exponent x in the above stated equation. So as I said, this is quite similar to example 5a, so I'd encourage you to stop the presentation and attempt example 6a, but I will show you the full work solution on the following slide. So here's example 6a, solution. So we're given the equation T is equal to m multiplied by k to the x multiplied by alpha. The T is equal to the torque. I've actually shown how we use the SI units to derive the dimensions shown here, but we can extract the dimensions for torque and also for angular acceleration, alpha, from table 2. Here's the table 2 extract. Here's the torque dimension shown here, and here's the angular acceleration dimension shown here. We know mass is a base unit having a dimension of m, and the radius of duration k has a unit of the meter, so the dimension will be m. Now again, we simply insert the dimensions into the above equation for torque, for mass, for radius of duration, power of x, and for alpha. Mass on the left hand side cancel with mass on the right hand side, t to negative 2 on the left hand side cancel with t to negative 2 on the right hand side. So we're left with L squared on the left hand side equals L to the x on the right hand side. Again, using the equating indices technique for dimension L, length, left hand side we have 2, on the right hand side we have x, equating indices. So in this case x is equal to 2. So we can now write the torque equation as T is equal to mk squared alpha. And here are some tutorial exercises related to dimensions problems. I'm going to outline them briefly to you, and then I will show you the full work solutions, but I'll let you review the solutions at your own pace. So here's exercise 1. The equation S equals to ut plus a half at squared can be written by dividing each term by ut. We're asked to show that each term in the equation is now non-dimensional. Exercise 2a, part 1. Given the definition that dynamic viscosity, mu, is equal to tau divided by dy by dx, where shear stress tau has the unit of the Newton per meter squared, and velocity gradient dy by dx has the unit of s to the negative 1 upon seconds. We're asked to use dimensional analysis to determine the unit of mu. Answer is given in the bracket here. And again, referring to an extract from table 2, here are the dimensions for shear stress. And obviously the dimension for the gradient dy by dx is going to be t to negative 1. Part 2 of exercise 2, if the kinematic viscosity is defined as nu is equal to mu divided by rho, again using dimensional analysis, we have to determine its unit also. Note that mass density, symbol rho, has the unit of the kilogram per meter cubed. And again, if we need to, we can find the dimensions for mass density in table 2. Dimensions for mass density shown here. Answer to part 1 shown again here, and answer for part 2 shown here. I would encourage you to start the presentation and attempt exercise 1a and exercise 2a, but the full work solutions will be shown on the following slides. Here's exercise 1a, solution. I'll let you review this solution at your own pace. Here's the first slide. Exercise 1a, solution continued. Here's the second slide. Exercise 2a, first part of the solution. Again, I'll let you review this at your own pace. Exercise 2a, solution continued. This is part 2. Again, I'll let you review this at your own pace. 2 further exercises. Exercise 3a, the stress in a leaf spring is given by sigma is equal to 3 times W times S to the power of A, or divided by 2 times N times B times T squared. Note that W is the applied force, S is the length of the spring, N is the number of leaves in the spring, and dimensions B and T are the breadth and the thickness of each leaf, respectively. We've got to find the value of exponent a. So again, that will be a question of inserting the dimensions, rearranging the equation appropriately, and equating indices to find the value of a. A is actually 1 in this case. And exercise 4a, more difficult question. The following equation occurs in connection with compressible flow in a pipe. So we're given 3 terms here. On the left hand side, first term is a squared multiplied by, in bracket, p1 squared minus p2 squared, and it's all divided by 2 times m squared times r times t. Subtract from that the natural log of p1 divided by p2, and that's equal to f times L times P divided by 2 times A. We're given in the question that A is area in meters squared, R is a constant unit is given as joule per kilogram per Kelvin, uppercase T is temperature, that's in Kelvin, lowercase p is pressure, that'll be in newtons per meter squared, uppercase L is length in meters, uppercase P is the perimeter of the pipe in meters, and lowercase m here is a parameter given in terms of kilograms per second. In part 1, we're asked to determine the dimensions of the parameter f, and a hint in the question, what is the dimension of the term natural log of P1 divided by P2? Well, obviously pressure P1 and pressure P2 have the same units, same dimensions, so they cancel, so effectively the dimension of the log term will be 1 or dimensionless. So for dimensional homogeneity, all 3 terms must be dimensionless. So we're asked to make use of this fact when finding f in the right hand term. Part 2, we're asked to show that this term, the first term on the left hand side of our equation, is also dimensionless. Just be careful with this expression because we have a squared and m squared, so when you insert the dimensions for a, which obviously are L squared, you will need to then square them. That's the third law of indices problem. Kilograms per second is the unit for m. You need to write that in terms of dimensions and also square them. So be very careful of that. And here are some hints for exercise 4 to help you develop your solutions. Because we know in this equation all terms are dimensionless, then for part 1, start from this equation, rearrange for the factor f, insert dimensions, the dimensions will cancel to show that the factor f is dimensionless. Exercise 4a continued. Further hints related to the solutions. This is for part 2. We have to insert dimensions into this term, shown here. The dimensions will cancel to a value of 1, thus the term is dimensionless. The answer for part 1 is shown here. I would encourage you to stop the presentation and attempt exercise 3a and 4a. 4a is challenging, but I would encourage you to attempt it. The full work solutions though are shown on the following slides. Here's exercise 3a, solution. There are actually 2 solutions to exercise 3. This is the first version. I will let you review the solution at your own pace. Note the dimensions for stress and for weight force can be extracted from our table 2. Also note in the question that the quantity t is squared, so of course we must square our dimensions. The question requires us to find the value of exponent a, shown here, and from the analysis a is equal to 1. And here's exercise 3a, an alternative solution to the problem. There's a slightly different approach here, but the answer for a, of course, is exactly the same. Here's exercise 4a, beginning of the solution. This is part 1 shown here. As I said previously, considering this term here has to be dimensionless, so for dimensional homogeneity, then all the terms are dimensionless. We need to go through the process and prove that f is dimensionless. So here's the approach used to show that f is indeed dimensionless, a value of 1 for its dimensions. Exercise 4a, solution continued. This is part 2. So again, we will know that this first term in the equation has to equal to 1 again. But I firstly need to determine all the dimensions for all the various quantities here. And that's what's been done here. And I'll let you review the solution at your own pace. In exercise 4a, solution continued. Now we insert all the dimensions to the term shown above and show that the term is dimensionless. Hence the equation is dimensionally homogeneous. Finally, I will leave you with some questions to attempt at your own pace, all related to the use of dimensions. Here's question 1a, parts A through to I, with the answers being shown in the square brackets on the right hand side. Essentially you have to determine the dimensions for each of the properties stated. All your questions on dimensions continued is question 2a. It has 3 parts. 2a. Answers to part A shown here, part B shown here, part C shown here. Tutorial questions on dimensions continued, and here's question 3a. Again, for you to attempt at your own pace. There are 4 parts to the question, and the answers are shown in the brackets on the right hand side. I hope this presentation has been of some use to you, and as always, thank you for viewing.